Hello, and thanks for watching my Module 2 presentation video. My name is Joshua Puhala. Um, I'm going to be doing a proof that shows that if x plus y is an even integer, then x and y must have the same parity. Um, the reason I'm doing a proof for that is because I initially selected this one. If x plus y is an even integer, then x and y are both even integers as well. It didn't take a whole lot of work into this one before I figured out that this is in fact false. Um, and I'm going to show why. Um, so again, I'll be showing that if x plus y is an even integer, then x and y have the same parity. Um, and what that means is that they can be either be both even or be both odd, but they have to be the same. Um, so I chose to do a proof by cases for this. I considered doing um, proof by contradiction, but this one only has a really limited number of possibilities. So I chose to just show all three options of what can happen with this. And so proof by cases was just easy to show all outcomes. Um, So jump into it. Case one is that x and y are both even integers. Um, so in this case, both x and y are even integers. Um, so we'll set them equal to 2k and y is equal to 2j. If we plug this in algebraically, so x plus y becomes 2k plus 2j, which you can factor out the 2 and just have it be 2 times k plus j. K and j both being integers means that k plus j is an integer. 2 times an integer is, in fact, even, which shows that x plus y is even, and there, yeah, I'm using this one. Shows that x plus y is even, and x plus y have the same parity. Let's go on to case 2, um, which case 2 is both x and y are odd integers. So we'll set x here equal to 2m plus 1 and y equal to 2n plus 1. Algebraically, that works out to 2m plus 1 plus 2n plus 1, which is 2m plus 2n plus 2. Again, you can factor out the 2, and m and n both being integers means that this inside the parentheses here is also an integer. 2 times an integer is an even integer. And our final case here, case 3, is actually a contradiction that shows that this is in fact true. So case 3 is x is an even integer and y is an odd integer, meaning that they do not have the same parity. X can also be odd and y can also be even. It doesn't really matter. So there's only two options. So if they're different, they're different. For this case, we'll do x is equal to 2p and y is equal to 2q plus 1. Algebraically, set that in here, and 2 becomes 2p plus 2q plus 1. You can factor the 2 out here, but then p and q being integers, that means that this is 2 times an integer plus 1, which is by definition an odd integer. So what I have here is basically the end of the proof, and it says that case 3 here shows that if the two integers x and y have different parity, they do not produce an even integer when summed. So I would say I didn't have a ton of difficulty with this necessarily, but I did run into that initial hurdle with kind of picking a false statement initially. So working through this was pretty interesting. It was fun to figure that out and then have to get my my proof reapproved it. um, yeah, so thank you for watching.